see what has always been there, but always out of reach, requires a specific kind of obsession. It demands a mind that refuses to accept that the boundaries of human sight are the boundaries of reality. In the mid-17th century, the world was expanding outward. Ships were charting vast oceans, maps were being redrawn, and astronomers were aiming massive glass tubes at the stars, mapping the craters of the moon and the rings of Saturn. The macrocosm was being conquered, but almost no one was looking down. No one suspected that an entirely separate universe, vaster and more populated than our own, was thriving in the palm of a hand, in a drop of rainwater, or on the surface of a human tooth. The man who would finally open that door was not a trained academic, a university professor, or a credentialed philosopher. He was a linen draper from Delft, a quiet trading town in the Netherlands. His name was Antonie van Leeuwenhoek. Born in 1632, Leeuwenhoek's early life gave no indication that he would one day rewrite the biological sciences. He was raised in a family of tradesmen. His father was a basket maker, and his mother came from a family of brewers. He received a basic practical education, but he never learned Latin, which was the mandatory language of science and high academia at the time. When his father passed away, a young Antonie was apprenticed to a cloth merchant in Amsterdam. By his early 20s, he returned to Delft, established his own shop, and set up a successful business selling fabrics, buttons, and ribbons. It was a comfortable, ordinary life. Many men would have been satisfied with this job, but for Antonie, a deeper curiosity was growing. Draper's survival depends entirely on precision. To judge the quality, thread count, and value of incoming textiles, merchants used small, rudimentary magnifying glasses. They were known as flea glasses. These magnifying glasses were weak lenses, capable of magnifying an object perhaps 3 or 4 times its original size, just enough to see the weave of a thread or the leg of an insect. For most drapers, the lens was just a tool of commerce. For Leeuwenhoek, it became an existential fixation. He became utterly consumed by a desire to see things clearer, sharper, and closer than any human being ever had before. Because he was isolated from the scientific institutions of London and Paris, he was unburdened by their theories, their consensus, and their limitations. He began to experiment with the very nature of light and sight. To understand how Antonie succeeded in seeing the unseen, one must understand the behavior of light itself, the science of optics. Light travels in straight lines, but when it passes from one medium to another, such as from the air into a piece of curved glass, its speed changes. This change in speed causes the light waves to bend, a phenomenon known as refraction. If a piece of glass is shaped correctly with a precise convex curvature, it can take the scattered parallel light rays bouncing off an object and bend them inward, converging them at a single focal point before they reach the human eye. This fools the brain into perceiving the object as if it occupies a much larger portion of our visual field than it actually does. During the 1660s, the scientific world was celebrating the English polymath Robert Hooke, who had published Microscope. It was a groundbreaking book filled with stunning illustrations of insects viewed through a compound microscope. Hooke's microscope used a system of multiple lenses aligned inside a long tube. Mechanically, it looked impressive, but optically, it had hit a physical wall. Early glassmaking was riddled with imperfections. Air bubbles, impurities, and structural irregularities were common. When you stacked multiple imperfect lenses on top of one another in a tube, the optical flaws multiplied. The images became blurry, distorted, and plagued by chromatic aberration, a defect where different colors of light bend at slightly different angles, fringing every image in a chaotic rainbow halo. Leeuwenhoek realized that the grand, compound microscopes of his era were fundamentally flawed. To see the truth, he needed to abandon the long tubes and the multiple lenses entirely. He needed to master the art of a single, perfect sphere. Working in complete secrecy, refusing to let anyone watch his work, Leeuwenhoek developed a revolutionary method for creating lenses. Instead of grinding down flat glass panels using abrasive powders, which left microscopic scratches on the surface, he took thin filaments of glass and placed them directly into a scorching flame. As the glass melted, surface tension naturally pulled the molten liquid into a perfect, uniform, microscopic bead. These tiny glass spheres, some no larger than the head of a pin, possessed an extraordinary curvature. Because the radius of the sphere was so incredibly small, its focal length was microscopic, allowing it to bend light with unprecedented, radical power. He mounted these tiny glass beads between two flat plates of brass or silver. To use it, you did not look down into a barrel. You held the entire instrument flat against your face, almost touching your own eyeball. Squinting through a pinhole directly into the light. On the opposite side of the plate, a tiny screw mechanism held the sample on a needle point, allowing the user to move the specimen fractions of a millimeter into focus. It was an awkward, exhausting way to view the world, but the results were miraculous. While Robert Hooke's celebrated compound microscope could magnify objects up to 30 times, Leeuwenhoek's simple single-lens devices reached magnification of 200, 300, and potentially 500 times life size, with a clarity that the world would not see achieved again for nearly 2 centuries. Armed with this unprecedented visual power, Leeuwenhoek began pointing his tiny silver plates at everything. In the summer of 1674, he took a vial of murky water from Berkel-Samara, a small lake near Delft, and held it up to his lens. He expected to see standard detritus, perhaps tiny pieces of decaying plant matter. Instead, he found himself looking into a teeming, bustling metropolis. He saw what he described as animalcules, tiny, elegant, living creatures moving with absolute intent and purpose. He wrote to the Royal Society of London, describing animals that were thousands of times smaller than a grain of sand, some rotating like tops, others darting forward with the speed of a pike, and some twisting like corkscrews through the water. He was looking at green algae, rotifers, and ciliates. He was the first human being to witness protozoa. His curiosity was insatiable. He examined the plaque scraped from his own teeth and the teeth of men who had never cleaned them. There, in the biological film, he discovered a completely different class of animalcules, even smaller, shifting and writhing in dense, chaotic clusters. He described them as moving like an eel in water, bending and flexing in place. Without knowing it, Leeuwenhoek had discovered bacteria. He looked at red blood cells circulating through his own veins, mapping the microscopic architecture of life itself. He sent page after page of meticulous, beautifully written letters to the high scientists in London. At first, they didn't believe him. They thought the uneducated Dutch draper was playing an elaborate trick, or losing his mind. They sent a delegation to Delft to inspect his instruments, and when they looked through his tiny glass spheres, they were stunned into silence. The invisible world was real. Today, the core principles of optics Leeuwenhoek harnessed remain unchanged, but the technology has evolved beyond anything he could have dreamed. Modern light microscopes have conquered the optical flaws of the past. We've moved back to compound systems, but our modern lenses are engineered using advanced synthetic glass composites and computer-calculated curvatures that eliminate distortion and chromatic aberration entirely. We use multi-element lenses that sync together perfectly, allowing a scientist to effortlessly turn a turret and jump from low magnification to a crisp, high-power view without losing their focal plane. Yet, even the most perfect optical microscope faces a hard boundary dictated by the laws of physics, the diffraction limit. Because visible light travels in waves, it cannot resolve objects that are smaller than half the wavelength of the light being used. Anything smaller than roughly 200 nanometers becomes an unresolvable blur. To break through this next frontier, modern science had to abandon light entirely. In the 20th century, we developed the electron microscope. Instead of bending photons of light through a glass sphere, these massive instruments fire a highly concentrated beam of accelerated electrons through a vacuum. Because electrons have a wavelength that is significantly shorter than light, They can be focused using electromagnetic fields instead of glass plates. This allows us to magnify the world up to millions of times its original size, letting us look past the boundaries of single bacteria to map the individual ridges of a virus, the structure of a protein, or the arrangement of single atoms. From a molten bead of glass held up to a candle in a dark room in Delft, to a multi-million-dollar electron microscope firing particles in a research lab, the journey of human discovery is a lineage of refinement. Antonie van Leeuwenhoek proved that if you refine the tools of sight, you refine the boundaries of human knowledge. He looked into a void of nothingness and found an infinite universe of life, leaving us with the permanent, haunting realization that no matter how closely we look, there is always an entire world waiting to be seen just beneath the surface.